Hi, everybody. It's time for Unit G. This unit's on wide column databases with emphasis on Apache Cassandra. All right, so let's roll down the agenda. We'll start by talking about what is a wide column database. We'll talk about the use cases of wide column. Then, as usual, like we've done with all the other databases, we'll look at the architecture of Cassandra and then how to query it. Mainly how to create tables first in Cassandra. Then we'll look at how to do CRUD, create, read, update, delete in Cassandra. And then we'll do a in-depth comparison of the wide column models and versus the relational model. And we'll talk about how you can design for wide column. And that'll be pretty much this entire unit. All right, let's start by talking about wide column databases. So what exactly is a wide column database? Wide column databases are also known as big table databases or extensible record stores. Generally, the idea here is there's just one large table with many columns in the table. And the model consists of multiple columns, and any column except the key column, of course, can have a value of null. And the idea here is you're going to be storing a lot of values across a column, and there's no table joins available to us. And in wide column, we only really store certain types of data. Like you're not going to store reference-oriented data at all in wide column. You're only going to store process-oriented data. That is, transactions or events or things like that. That's the kind of stuff that gets stored in wide column. Generally categorical type data like customers, not really relevant for wide column. You can certainly do it. You can store anything in a table, right? It's just that's not the best use case for wide column. In the cloud, we have lots of different wide column offerings. We have Azure Tables, Google Bigtable, which is really sort of like the first wide column database. DynamoDB from AWS, and in the Hadoop ecosystem, there's an application called HBase, and HBase is a wide column database that runs over HDFS. So here's a visualization of how wide column works. Here's a table, and this table is like any other relational table. And if this were stored in a row-oriented database, it would be stored a lot like the way you see it here. Okay, we would be storing this, then the next thing in the file would be this, then the next thing in the file would be this, etc. The way a wide column database stores this same table is it would store a table for each column. And each column has what's called a row key. And then within that row key, you have the attributes in this column. And then this row key in this table has only the attributes for this column. So you see, if you have a lot of nulls and you have a lot of columns, this ends up being a tremendously efficient way to store your data. Because if you're just looking for freshmen, you don't have to scan through all 6 columns to do that. You can just scan through the 3 columns that are stored in this particular mini table of just columns, right? Of just the year column, I should say, of just the year column. Likewise, if you want to get an average GPA, you don't have to go to this row and then jump to the GPA and then tally that, and then go to this row and skip it, and then go to this row and then jump to the GPA and tally that. You can just go to this mini table and then just average all the values that are in the mini table. So aggregate operations, much faster in wide column. Searching, filtering by a single column, grouping by a single column, or grouping by even 2 columns is much faster in wide column. You can already probably see the downside to a wide column model. If I go to add a new row, I have to add it to this table and that table and that table, right? If I want to add a year, I want to update Dave to give Dave a year, I'm really adding a row key to year with the new year, right? So I would add a 4 here and then sophomore to add Dave. So things work a little differently in wide column. The good news is this is all transparent to you. You just have to know that this is how the internal stuff is stored, and you really don't have to worry so much about that. It's not like you'll have to figure out which column things are in or anything like that. It works just like SQL does. Okay, here's some use cases for wide column. We have storing a lot of data, a lot of immutable data. That is, it's create, read. Okay, we're not going to do any updates or deleting. And it's process oriented, like orders, scanning concert tickets, vehicle movements in real time. Your Amazon, you're processing a lot of orders. All of those would be great use cases for wide column. Any kind of time series data, like you got a bunch of IoT devices, and they all are reporting a environmental, like temperature, weather, pressure, humidity, and every 10 seconds they are generating that data. That data never updates, right? It gets created and then it gets written. So wide column is 100% and an appropriate use case for time series data for that reason. We're never going to go back and change that temperature to something else at that point in time. So why use a database that supports that? Now, certainly wide column does support that, but it's just designed so that you don't need to do that. So fitness tracker data, weather data, user activity data, this all stored in wide column. My bet is if you look at any of these fitness trackers and how those companies are storing their data, I would almost guarantee that they're using some kind of wide column database. If your application has a very specific query flow, you can design your wide column to support query. And when you're designing an application around wide column, you do need to think about the queries that you are posing in the application. For example, you might search for a region, then select a hotel in the region, then select an available room by hotel. And each one of these would be a wide column table. So you might have one table that has a big pile of regions in it, and then you search for a region, and then that gives you back a region. And then you have another wide column table that has just all the hotels within that region. And then you can use that table. You can use the region that you selected as a filter on the hotels within the region. Then you would have another wide column table that would have the rooms in all the hotels. And then that table would allow you to select a room by hotel. And if you think about this, if you're talking about every hotel in the world, the amount of data is massive. And because it's so large, we don't want to just store every single one row for every single hotel room. We don't want to store one row for every single hotel room in a single table, right? Because that's a lot of data. But in wide column, you're still doing that. But what wide column lets you do is partition. So I could partition the data in a way that each hotel is in its own partition. And so when I get down to the point where I'm actually selecting a hotel, I'm not competing with everybody else that's selecting a hotel, because the odds of everybody in the universe going to that one hotel is very slim. And that's the basics behind how wide column achieves massive scale. It does a good job of it as well. So the good and bad of wide column. It's really good for time series data. When you need to have what are called guaranteed writes, you want to make sure that data gets written, and you want to be 100% sure the data was written. And you don't want to have a situation where a table lock causes it so that you can't write data. There's no locking at all in wide column databases. They are base. They are not ACID. They are all eventual consistency systems. You have high write volume, process-oriented data, or queries across a single subject, like I'm looking for orders, or I'm looking for trips. I'm doing a rideshare app and I need to search through trips. It's not good for General purpose database design, like the things you do in relational, like, oh, well, I got these orders. I want to see how many people bought this product, or how many times this customer made an order, those kinds of, or how many people buy things on a Wednesday. It's not that kind of database, and it's not going to be good at doing these ad hoc queries, querying things any way you want. You are going to be limited as to how you can retrieve the data back out. So it's not good for that. It's not good for data warehouses. Again, data warehouses are these cross-cutting databases where, one time I want to say, give me the total amount of orders that Mike Fudge has placed, and the other time I want to say how many people are buying this particular brand of sneaker, right? And then another time I want to say, on a Monday when it's raining, how many people are buying umbrellas, right? These are all different dimensions that we're exploring our data across, and you cannot design a wide column database to do that and be successful at it. It'll just be incredibly slow and need to fetch more data than you want. If your data has to be normalized, if there's a requirement that says gotta be in third normal form, or even gotta be in second normal form, then this is not for you. Most of the data that you're gonna see in a wide column is like completely denormalized. It's not even in zero normal form. It's not even in first normal form. It'll have repeating groups of data. It'll definitely have partial dependencies. So wide column is great if you don't understand any normalization and you understand the use case for wide column, because there's really nothing more than a huge table that everything goes in. And so one row means something, and then you sort everything associated with that row in that table. So reference-oriented data is out. Not going to use reference-oriented data. So typical applications of wide column: any time series, IoT applications, tracking user activity, performance monitoring. You can already see these are all process-oriented activities. This is all process-oriented data. So social media analytics, e-commerce transaction, messaging, also telemetry. Like, how like when you install an app, it says, we're going to track what you do in this app. Do you want to opt out of this? Yes or no? That's called telemetry. What happened is that app is recording your touch points and then sending those to a database so that they can figure out what you're doing in the app and how to improve the app. Okay, let's take a look at Cassandra. Cassandra is a open source wide column database originally developed by Facebook and open sourced in 2008. It was based on the Google Bigtable and Amazon DynamoDB papers. So really, Google and Amazon sort of built wide column and had a theory behind wide column and then implemented it in the cloud. And then Cassandra was the first offering of this that was not cloud oriented. Cassandra is what's called a base system, which means it uses eventual consistency. And when we have eventual consistency, what we're saying here is we can always write, okay, but we're not guaranteed to be able to read out exactly what we wrote. And we're going to learn why this is, and we're going to also see that, in a way, this doesn't really matter. We're okay with this. This is not something that is going to be a big problem, if you will. You might say, well, hold on a second. You mean I write an order and I can't immediately read that order back out? And the answer to that is yes, in some cases. But think about this. If you're distributing your orders and I write an order, I can read my order back out, but somebody else can't read my order back out. But who cares? They don't need to read my order. So it's all about design. If you design around eventual consistency, you can leverage the power of the fact that you can achieve a massive amount of writes at scale, and never have to flinch about causing locks. Another great example of this is because it's right now it's around March Madness. So all these games are going on. There's live stats going on. This is a great application of using a wide column database. If you're going to need to store those individual events that happen during the game for longer than the game is over, right? If you're going to only do them during the game, you don't need to store them in a wide column database. But imagine that live stream of data at every game, and every game is writing to, in essence, the same database. We partition that database by game so that any one game is only writing to its own little place, but later on I can read them all out from one massive table. So that's why they call it a big table database. So Cassandra has a, it uses the wide column data store model, and it has key maps, and we're going to key selection is really what makes Cassandra go. It has an SQL-like query language called SQL, CQL, Cassandra Query Language. The tables have to be there prior to being stored, so it's not like MongoDB where you can just say, I feel like storing this, store it, done. It does have a schema, and you do need to create the schema before you can store data in there, but there are no data integrity constraints other than primary key constraints, and there definitely are no table joins. So database is the Cassandra way. How you're going to get the information out, that governs how you build the database in Cassandra. So again, we're going to have redundant, denormalized data. When you fetch a row, it's going to give you everything you could possibly need to answer that query. And we're going to build this one large flat table. All right, so you might be saying, well, how does it achieve writes at scale? And the way that Cassandra and all these other wide column databases achieve writes at scale is they use a distributed architecture. So in Cassandra, they use a ring architecture. And in the Cassandra ring, every node plays the same role. And the nodes all talk to each other. So everybody knows what's going on. And unlike other databases, there's no single master here. So you can say, hey, this node, write data, or hey, that node, write data, and it will write the data for you. And then eventually this node will talk to the other nodes and say, hey, I've got Mike Fudge's new order over here. And then that way when you ask this node might say, well, I don't know anything about Mike Fudge's order. And then if you ask it a few seconds later, it'll say, oh yeah, I know something about Mike Fudge's order. So that's the idea behind eventual consistency is you're guaranteed to be able to write because everybody belongs to their own node, and you're distributing the data in a way so that if you design correctly, you're distributing the data in a way so that no two people are writing to the same node, right? Or even if there are multiple people writing to the same node, there's few of them, there's not a lot of them. That's number one. And then number two, the eventual consistency means when I write to this node, if somebody else immediately asks for my information about what I just wrote, and they go over here, they might not know about it yet, but they will at some point. And you usually don't care about immediacy, right? Eventual consistency could mean in a fraction of a second later. Okay, what it just means is not the moment it was written. Okay, and that's something to recognize is eventual consistency doesn't mean next Thursday. Okay, it doesn't work that way. It's much faster than that. Okay, so again, that data gets replicated, no single point of failure. I can scale easily. If I find that this isn't working, I just add more nodes. And you can in essence auto scale your ring architecture if you want. So like it's Christmas time and it's the holiday season and everybody seems to be buying everything. So what you could do is you could scale from a 50 node ring to a 500 node ring. And then when it's all over, you can scale it back down again. No worries. Another thing that you can do with the ring architecture is you can set how many replicas you have. So I can write my order here and then say, I want to make 3 copies of that. And it'll write it here and then put a copy here, here, and there. And so you can give yourself some fault tolerance here by spreading out the data over the ring. Another neat thing that you can do with Cassandra is you can have multiple rings. So I can have this ring living in North America, and then I can have another ring in Asia Pacific, and then that way anybody who's writing data in Asia Pacific writes to the Asia Pacific ring, and then people in North America are writing to the North American ring, and then there's a way to replicate between the rings, and that might occur less often, like every 3 hours. So there's lots of really cool ways that you can build this out. And the thing to remember is that from your perspective, you're going to see a table called orders, and it's going to have Asia Pacific orders in it, and it's going to have North American orders in it. And you'll query it, and you'll see data, and then you'll query it later, and you'll see more data, but you won't know exactly when that data was added unless there's some kind of timestamp in there, right? But the point is like if somebody in Asia Pacific writes an order and I query it in North America, I'm not going to see it immediately, but that's okay. But I will see it eventually because it will guarantee that the data gets written. All right, let's talk Cassandra data model. So here's the data model at a glance. As we said before, we're going to have a cluster, and a cluster is a ring of nodes. And then what we'll create on that cluster is a key space, and a key space specifies two things: the replication strategy and the topology. Okay, so how many nodes in the ring and how many nodes are the replica. Key space is the equivalent of a database in Cassandra. The difference is you must specify the replication strategy in the key space. This is basically how you're going to get massive scale. Now, in this class, in our demos, we have a one node Cassandra cluster. We can't really it doesn't make a lot of sense when it's running in a container on one computer to have a 6-node Cassandra ring. As much as I'd like to do that, we probably don't have enough RAM on our machines to do that. So we'll run things with a 1-node ring, but we'll be able to still see the benefits and drawbacks of how ring architecture works. So in the key space, you create a table, and this is exactly the same as a DBMS table. Same idea. There's rows and columns, and columns that aren't key are always nullable. We have to specify for every table a row key. This is just like a primary key. The only difference is that you have to specify a partition key and a cluster key. And if you only specify one of these, it functions as both. So if I just said, int identity or whatever, which they don't really have in Cassandra, and then I said that's going to be my only key, that key functions as both a partition key and a cluster key. So what the heck is a partition key? The partition key determines which node in the ring the data gets written to, which node in the key space, technically, the data would get written to. And the cluster key determines where, that's pretty much like the primary key of the table that only exists, the part of the table that only exists on that node. There's also indexes in Cassandra, which work just like an RDBMS index. You can use them to query data that you don't have a key on. That way, if you need to query data and not use the key, you can. So let's look at key spaces. It's more than just a logical container like you would have with a database. You also need to specify a replication strategy and a replication factor. So there are really two basic replication strategies. There's the simple strategy, which is the only one we will use in this class. And then there's the network topology, which you can define, location-aware topologies. Like you can say, define this as New England, and then set up how many nodes are in New England, and then say, and now define this as California, and set up nodes in there, and then specify how they replicate from one piece of topology to the other and how often. Okay, let's do a demo. I think it's time for a demo. Let's get in here and connect to the Cassandra shell, which is CQLSH, and we'll take a look at some key spaces and then create a key space for our demos and then use it. Okay, I'm out here at the command line and I'm ready to connect to, let's just show you here. I have Cassandra is up and running here somewhere. There it is. And let's connect to the client, which is conveniently also on the server. Okay, I'm connected into the Cassandra client, and let's do this. Let's do show key spaces. Okay, I don't have a show. Let's do help. All right, and there's describe. So let's try that one. Describe key spaces. Okay, and these are the key spaces that I have. And you see I already have that sysmon key space because I did this before. So I'm going to drop key space, sysmon. Okay, I just got rid of it. And now I'm going to recreate this key space. Let me zoom this in just a little bit. There. So I'll say create key space, sysmon. That's the name of my database, if you will, with replication. And then the replication class is going to be simple strategy. That's all we'll use in this class. And then my replication factor is going to be 1 because I only have one node in my cluster. It doesn't make sense for me to have a replication factor higher than that. All right. And then I'm going to use sysmon. And now I'm in the sysmon key space. And I can do show tables. Is there a show tables or is it describe tables? I forgot. I think it's describe tables. Yeah, and there's no tables. All right, so I basically got into Cassandra and was able to set up my key space. All right, let's talk about tables and keys now. So your tables in Cassandra, very similar to relational tables. You are going to have columns that you're going to create, and there's data types and all that stuff. Again, I can't emphasize it enough. There's no table joins. So normally you're going to have an incredibly flat table design with a lot of columns, but this is why it's called wide column. Again, we want to capture events, orders, reading, sensors, things like that. You don't want to put customers in here. That's not the right use case, even though you can. That's why in here, when I do examples, I won't use that kind of data. I'll always use process-oriented data to give you a real feel for the proper use cases for Cassandra. Okay. All the columns that aren't the key column are nullable. Okay, and there's no integrity constraints. I can't put a check constraint or anything like that on my data. It's not possible. Okay, we use create table, and here's the docs on that. So let's talk about some column data types. We have int, big int. Int is 4 bytes. Big int is 8 bytes. You have varchar or text. You don't have to specify how large the varchar is. It's as big as you need it to be. We have decimals and double precision values. We have timestamp and universally unique ID and time universally unique ID, which is a timestamp that is conflict free and it will always be higher. Every time you get a new one, it's higher than the next one. So it's the perfect int identity in Cassandra. And time UUID is a great cluster key. It's not a good partition key at all, but it'll be a good cluster key. And then there's also things like date, Boolean, float, the things that you already know and love and are familiar with in other database management systems. There's also some collection types as well. Like, again, because everything goes in one table, there's other data types that are useful for when you have to embed complex objects into a column. So you can have a list type, which lets you denormalize, a set of values. You can have a map type, which is useful for creating like a, embedding something. Like if I have an order and I want to embed all the customer information because it's one order, one customer, right? So one order, one customer. So why not just take all that customer information and embed it into a map type? And then there's a set type, which is pretty much like a list, but there's no duplicates. Okay. The number one thing you want to know about Cassandra is row keys matter, and your choice of row key will limit how you can retrieve the data back out. The first attribute in the row key is the partition key. The partition key is any value, but it gets hashed, and then that hash determines which node in the ring, which node in your table space ring the data will get written to. Okay, and this is very similar to what we saw with a MongoDB shard. Okay. The cluster key, generally you want this to be, in ascending order, because this is how it physically gets written to that node in the table space. So that cluster key is going to determine where the data actually gets written on the node, similar to a DBMS clustered index. Okay. And to retrieve the rows, you must use values from the row key. Okay, so you can't get away with just trying to, look up someone's name or something. That's not going to work. You have to provide the partition key and to some degree the clustering key. We can create indexes and stuff so that you can use the partition key and a different key to retrieve like a name. But you're definitely going to need the partition key so that you can figure out which node has the data. So again, partition key distributes data across the nodes. Clustering key sorts the data, stores the data in sorted order within the node. All right, let's walk through a little animation that shows you how the Cassandra cluster actually writes data to itself. So here we have 3 nodes in a key space, and we're going to write cars. And the partition key is the car's make, and then the cluster key is the car's model. Now, these are probably not great keys, but it's perfect for demonstration purposes. So we go to write the first one, and the ring chooses to put that on node 1 based on its hash of the make. So the one thing you're guaranteed is all the Chevys are going to now be on node 1 because that's what the ring has decided to do. So our Toyota Prius, that just so happens to land on node 2. It could have landed on node 3, but the way it got hashed, it landed on node 2. So now you know that all the Toyotas will land on node 2. Then we got a Chevy Cruze, and you see that that goes on to node 1, and it goes in front of the Volt because this is the cluster key, and things are stored in the cluster key in order. And so this is why your choice of cluster key needs to be something that is probably naturally ascending, naturally occurring in ascending order. This is going to be important to performance in Cassandra. Then we get a Jeep Wrangler, and that just so happens to drop on node 3. It could have dropped on node 1 or 2, but this is where it ended up. Then a Ford Fusion, that just so happens to go to node 1. Toyota Camry gets put in front of Prius on this node. Jeep Compass gets put in front of Wrangler on node 3. Okay, let's do a demo where let me turn my head off. Let's do a demo where we make a table and take a look at the table and then insert some rows into the table just to see what the heck happens. Okay, and we'll demonstrate that this uses what's called an upsert pattern, which means when you go to insert it and it's already there, it just updates it. So this will help you really get an understanding of how Cassandra works. Really base level. Okay, I'm back out again at the Cassandra client, and let's just use the sysmon database key space because that's where we're at. And let's create a table here. Create table users. Again, this is a horrible table, but it's just for an example. And then I'm going to say name is text, and I don't have to put in. If I did varchar, I wouldn't have to put in a size either. And then I'll have age as an int. And then I'll have primary key name. Now, because I did not choose, and then let's do describe tables. And there's the users table. And then I'm going to say describe table users, and I'm going to get all sorts of info on it. And you'll see that here's the columns. And we've got just some statistics here on those columns that you can look at here. Okay. And let's do some inserts. So insert into users name age. Then let's insert values. Mike. Good old Mike is 51. Okay, and then let's select. And there I am. And if I insert me again, and again, and again, and again, and again, and again, I'm only in there once. Okay, so this is the first thing to know about wide column. At least the way Cassandra implements wide column is there is no, you can insert the same thing multiple times and it's just going to update it. To show you that it updates, let me change, now I'm 52. 52. It doesn't update, right? So an insert with the same key doesn't update. An insert with a different key, inserts it again. That's fine. Right? But insert with the same key will do an update. And this is kind of an important concept to wrap your head around when you're using Cassandra. This is super handy, by the way, because when you're batch loading in time-oriented data, like imagine you have some IoT sensors and things go wrong and it's not loading into the database anymore and you need to reload a whole bunch of data. You don't have to figure out exactly when you left off. You can just say, let's just go back a week and reinsert. And it's just not going to have a problem with that. You're not going to get duplicate data or anything like that. You don't get an integrity key constraint when you try to insert the same data. And this is actually very convenient and handy. Like I said, there's no way to put any check constraints on here, so there's nothing preventing me from putting in whatever I want as long as it matches the data type. As long as it matches the data type, it doesn't matter. Now, one thing we haven't really seen is how is Cassandra different than a regular relational database, because right now it doesn't seem to be any different other than the fact that you can insert the same value more than once and it won't complain about it. But we'll get there. All right. To really understand Cassandra, we're going to have to move to a better use case, an example than just creating a users table. So we will use that sysmon table and fill it in with telemetry data about computers. And to understand queries the Cassandra way, you really have to have a good understanding of the partition key idea. So the partition key is where our data actually gets stored on the nodes that are in that key space, the ring nodes in the key space. So every select statement must include a where to target a partition, to target one or more partitions. If it does not, we are then reading the entire contents of the cluster to resolve the query. And this is what we call an anti-pattern. And you really need to avoid this, okay? And it's hard to sort of explain this when you've just got a single node of a Cassandra cluster, but think of the use case of Cassandra. You're going to have a key space that's going to have 50 nodes in it. And every node is going to have when someone placed an order on it. And if you ask for all the orders on a Tuesday, it has no choice but to ask every participating node in the ring for that data, which means you're going to ask 50 nodes, give or take, depending on your replication strategy. Probably going to be a little less than 50. You're going to ask a lot of nodes for all that data so that it can figure out which data needs to be included in the query. So it might have to ask 25 nodes, do you have the data I need? Do you have the data I need? And then it has to somehow assemble that. And because there's no single master, it has to shuffle that data around to the node in which you ran the query on. And so this is, we consider this an anti-pattern, and you don't want to do this. So you need to think about your design, because the choice of partition key is going to limit the kinds of queries that you can write in Cassandra. Okay. Again, everything you do has a pro and a con. This would be the disadvantage / the con of using Cassandra. So let's do a demo of this. Let's move on and try this in a demo. Okay, let's start by getting some data into, making our table and getting some data into it. So I've pasted in some code here to do my create table. And I have, this is going to keep track of metrics on a computer. So I have the name of the computer, host name, the operating system as text, the timestamp that that particular value was measured on, and then a how much CPU was being utilized at that point. So this is really the metric that we're measuring, and all of these other things are really just sort of categories, and then my partition key will be host name, and then measured on will be the cluster key. And usually we are going to use some time-oriented field as the cluster key, by the way, because think about it, for any given host on my cluster, this will guarantee that I am adding those at the end, because they are increasing in over time. Okay, so I've made that table. I can describe that table just to make sure it's there. Yeah, I got to spell it right. There you go. Table's there. Let's insert some data. So in order to speed this up, I have a couple of insert statements here that I've already written. Okay, I'm going to just copy these. You can get these right from the PowerPoint slides as well. Paste those in here. Hopefully they go in. And it looks like all the inserts went in. And so let's just do a select everything from system utilization. Now you'll see that I have the partition key is in red. The cluster key is in cyan, teal. It's a teal color. And then the other columns are just in purple. And this is the partition key, and this measured on is the cluster key. All right. So, you might say, well, hey, Mike, I can do select star and it doesn't throw up a problem with me. Yes, you can do that. But again, it's looking at what's on one of the nodes when you do this. Okay, it's not looking at all the nodes. It's just looking at one of the nodes. Okay, that's the first thing you want to know about that. So let's inspect what works, what doesn't work. So one of the things you might want to say is, hey, what are all of the measurements on the host name Mars? So you would do select, star from system utilization where host name is Mars. And this will give you all the measurements on Mars, on the host Mars, not the planet Mars. And you'll see, here's the different measurements and the different times that they were taken. Yay. Okay. Now you might say, well, cool. Maybe I want to see only the measurements on Mars, where the measurements were after, oh, I don't know. Maybe the measurements are after, let's say 2018, 07, 19, and let's say they're after 9:30 a.m. And so that works, right? Again, this is the partition key. That's the cluster key. As long as I'm messing around with those, things are right as rain. Let me show you what doesn't work. Can I do this? Can I just say, give me all of the measurements that are across any host that are after 9:30 on the 19th? Can I do that? And you'll see that you can't do that. It says, can't execute this query. It involves data filtering and thus will have unpredictable performance. Okay. What does this mean? This means that it has to ask more than one node that you didn't specify to participate in this query. And therefore, it will have to ask the nodes to participate in the query and then collect the data from the result of that participation and then send it to your node that you're requesting this query from and then produce the output to you. This is messy and can give you really bad performance, especially when there's a lot of writes going on. And the whole point of wide column is we want to have massive amounts of writes. We want to be able to support high writes, and this type of activity is not conducive of that. So how can you, if you really want to get around this, you can add allow filtering at the end. And then it works. But what did you just do? You just said, go to every node and run this where clause on that node in my ring, figure out what the output is, send that back to the node that I'm connected to at this particular time, and let that node figure out what rows it should show me. And while you're doing that, there's a whole bunch of writes going on, so good luck. Hopefully you don't have to wait for those writes to finish before you can get what you need. All right, that's why you want to avoid allow filtering at all costs. It's one thing when you're just playing around and looking at stuff, but you don't want to include this in your queries when possible. You want to write your query, you want to design your tables so you don't need this. And if you do need it, then you want to create indexes or something like that to avoid doing this. So let's find the limits where let's hit a bunch of things that cause allow filtering. Okay. So that causes allow filtering because it doesn't have a partition key. But what about something like this? What if I said where host name is Mars or host name is Venus? Is that going to allow filtering when I ask to participate across two partition keys? I can't do an OR. Doesn't let me do that. There's no way that you can do an OR in Cassandra, and there's a good reason for this, and the reason being is that you have to get one more node involved in the process. I wonder if in works. I wonder if we can use like something like hostname in and then specify a list like this. Oh, I'm just trying. I'm just trying to show you what may or may not work. You know, it gets you thinking about stuff. Okay. I think it's like this for lists. By the way, it's like that. That works. All right. So or, there's no or, but I can ask for set inclusion, and that does work. And by the way, if I have a host name that doesn't exist, like Mars and Mark, it still works, and it doesn't give me an error. It's just I don't have any Mark host. So it works. So again, if you want to have more than one node participate, you need to use the set operator in. There is no or. There is no or in Cassandra that you can use. So make a note. What else causes allow filtering? Well, maybe I want to just get the Windows computers out of here. So I say where OS is Windows. This is not a partition key and it is not a cluster key. So this is going to say, yo, I can't do this. Got to allow filtering. My head's in the way. Got to allow filtering. See that? Can't do it. Now we're going to learn later on how you can make this query go without allowing filtering by adding, you know, a materialized view or an index. Okay, but we'll get there. So what other things can I show you? Well, this one won't work either, right? So even if I include the partition key where host name is Venus, that's going to work, right? Because that just pulls it right off one of the nodes in my ring. But I can't say and CPU percent is more than 50%. I can't do that because this is not a cluster key. It's not a partition key. It's not indexed. So if I did want to see that, I would have to choose allow filtering. Again, well, maybe I should lower that number. 25%. Wow, what's the CPUs on V? Oh, they're very low. Let's say, let's change it the other way. Okay, now we see data. My point being, when you run this command, even though it is limited to a single host in the ring, right? It's a single node in the ring participating because we asked for one host. It still has to include allow filtering because we have to scan all the rows on that node for this matching criteria. And that is a expensive operation. Again, you have to kind of go back to what we learned in IST769 about indexes to really understand in depth what is happening here, right? So again, on that node, we have just data put on there. And unless you're going to retrieve that by this key, you're going to have to incur a table scan, in essence. And what Cassandra does not like is table scans. Okay, it can do an index scan, but it doesn't or an index seek, but it doesn't like table scans. And so you cannot do a table scan. And because this is not part of any key, it will be a table scan, plain and simple. And that's no bueno in Cassandra. All right, I talked a lot about allow filtering already, but let's just do it one more time because it's so important to understand. It's incredibly important to understand. If you really want to pass an interview where they ask you about Cassandra, you better know the Cassandra architecture and the issues associated with it, right? Basically, if you are not part of the key, if you aren't part of the key, then you are going to incur either asking more than one node in the ring for data, if you're not part of the partition key, or you're going to ask a single node in the data to do a table scan, and either of those are not socially acceptable by Cassandra. Okay, we do not want to allow that in Cassandra, because those are incredibly costly operations. They must incur locks, and locks kind of go against what we're talking about here when we're talking about eventual consistency. Right? There's no other way. I mean, I guess you could go through it, but the way files get read and written, the file is going to get, it's not a database lock. It's just the fact that the file is being read at this point. And because it's being read off of disk, somebody can't write to it while it's being read. So we want to avoid allow filtering at all costs. And there's a couple ways to do this, but the most important way that you can avoid allow filtering is to make sure that you include what it is you're filtering for in the key. So if I'm going to search system utilization by year, for example, like I need to put in the year. So I want all the telemetry from 2022 or 2018, then I should add another column, year, and then add that to my key. And this is like an acceptable thing with Cassandra. You keep your query use cases in mind and you design that table accordingly. And that's basically what you want to do. And if you have several use cases in mind, then Cassandra is not the solution for you. Okay, you need to sort of think through. Maybe you collect the data in Cassandra and then you ship it to some other database like Elasticsearch, where Elasticsearch is designed to sort of query anything. And that's maybe a better strategy. All right, let's talk secondary indexes. Secondary indexes allow us to take those cluster keys and now do a search where we include the partition key, but include another column that is not the cluster key. Okay, so it avoids doing the table scan thing that we talked about before. Okay, this is incredibly useful for columns with low cardinality, right, whose values seldom change, right? Secondary indexes do not affect the partition key, only the cluster key. And by covering the column with the partition key and the secondary index, we can get around using allow filtering. And this works a lot like a relational index. You say create index, name of index on table, and then you include the column that you would like to be, the column or columns that you would like to be the index keys. And that's the gist of secondary indexes. Again, the secondary index does not do anything about the partition key. It only allows us to query based on different columns that are not that cluster key. All right. How about a demo? So we'll do a nice demo here where we go ahead and monkey around with some secondary indexes. We'll also show you how to see the index with describe and demonstrate that it now works without allow filtering. Okay, I'm right back here out at my Cassandra command line. And let's do this one here. Let's say your host name is Venus and your OS is a Mac. Let's do something that's a little more interesting. Let's say your host name is Saturn. Your OS is Windows. And, right? Can't do it, allow filtering. So let's put an index. Let's put an index on OS. Let's put an index on OX. So let's do this. Create index IX system utilization OS on system utilization UTILIZation, and then we're going to put it on the OS column. Okay, and then let's do this. Describe whoop, let me just do it this way. Describe system utilization. Now there's an index. See that? And it shows us that there's now an index on that table. All right. Now that we know there's an index, let's see if we can use it. So the same query before that said, I need filtering. Now it doesn't need filtering. Why doesn't it need filtering? Again, because there is a way to retrieve these values without doing a table scan. Right? It can use this index to retrieve the values, right? Still doesn't help me with CPU percentage and CPU percentage is a 5, it still won't work because there's no index on this one. You know what else won't work? Just asking for the Windows hosts. Oh, wait, that does work. How cool is that? Why does that work? Well, I'm glad you asked. Here's why it works. Because we can use this index here to ask each node to retrieve the values based on that condition. Just like we would when we asked a couple of partition keys. Where did I do that? Right here. When I asked a couple of partition keys to participate. So that's really handy. We can do that. Let's add another index just for grins. Let's add another index here. And let's add another index on CPU percentage. Let's put in CPU percentage here. And then let's try this, where CPU percentage is bigger than 25. Oh, now see, now that doesn't work. Now think about why this one doesn't work. Let's go back here and let's try CPU percentage equals 25. That one works. I'll show you. Equals 5. There's a couple that have 5%. That works. But this doesn't work. And that should give you a little bit of a hint as to why this works on an index. Because the index can match exactly this value. And it knows exactly what to retrieve. It's called an index seek. Right? It can do an index seek. You can't seek multiple values. So you must still do a scan. So in order to make this work, I'm pretty sure I need to include the partition key. And host name is Mars. Let's see if this works. That still doesn't work. That works, but it still won't work with that greater than. And that's because we are still doing a scan instead of a seek. And unless I can somehow get around that, I am not going to be able to do that kind of query. So one thing indexing will do is increase the ability of you to be able to query the table based on an exact value, OS Windows, CPU percent 5, right? Because now it can do a seek on that index, and it even will work across partitions. But what you still can't do is some kind of weak match or pattern match on there, okay? You can't do not equals, by the way, in Cassandra, because again, this has to do with indexing, right? But I wouldn't be able to do, I don't even know how to represent this with a varchar, greater than, right? Can't do that, okay? So unless it's an exact kind of match, you're not going to be able to leverage that index. All right, let's talk materialized views now. So a materialized view is a Cassandra managed table that is dependent on a base table, okay? We use the materialized view to rewrite the partition key. So if you want to change the partition key, you use a materialized view. So same table, but now it's queryable by a different partition key. Okay. And then Cassandra is responsible for making sure that whenever you insert or update data, it keeps the materialized view in sync with the underlying data in the table. Okay. And so the requirements of any materialized view are we must include the primary key of the base table in the materialized view. And we must make sure that the values that we are adding to the new primary key are not null, right? You can't, because that's by definition of a key, it can't be null. So the materialized view command looks something like this. You'll create materialized view as the name of it, and then you'll have a select statement where the columns, where all the key columns that you're going to include in the new key are not null. And then the new primary key is going to be the new partition key, and then the original key columns are now cluster keys. Okay, the new key columns are now cluster keys. So let's do this. And what we'll do as a demo here is we'll drop the indexes, because that will make things easier, because we only have so many columns in here, right? And then what we will do is we will make a materialized view instead on the OS. And I'll show you how that ends up being different than what we had before. And I'll also demonstrate that if we insert some new data, the materialized view still works. Okay. Okay, I'm out here at the command line again. First thing I got to do is drop my other indexes. Drop that index. And I need to drop the other index. Okay. Now the indexes are gone. Let me just do a describe to show you that they're not there anymore. Where's my describe there? Okay, no more indexes there. Let's create ourselves a materialize view. So create materialize view. System utilization by CPU percent. System utilization by CPU percent. I could actually do it by OS, but I'll do it by CPU percent. And now I need to give it a select statement. So select from system utilization, where the column that I'm going to make key is not null. Need to do that. And the other columns that are already key, this is kind of silly, but you got to do it, and host name is not null, and measured on is not null. You got to do that for all of them. I know my head's in the way here. Let me get rid of me. Bye, Mike. Oop, wrong button. There. So I need to do that because this is going to be the new partition key, and these are the old partition and cluster key. And then I say primary key of this new guy is going to be the CPU percent. That is now the new partition key, which is kind of a silly partition key, but you can do it, right? That's the new partition key. And then the cluster keys are now host name and measured on. Okay, and these are not in production yet, but this is let me show you a describe. And now I have a materialized view. I have the table, and then hanging off that table is a materialized view. And this is like its own little table. By CPU percent. Boy, I got to spell it right, don't I? I'm going to give up. I'm going to just throw the white towel in there. And now you look, and the partition key is now this. CPU percent is now the partition key. And then these two are the cluster key. Now, why would you ever want to do this? In this example, you probably wouldn't want to do this, but think about you're designing your Spotify, right? And you've built your table based on user, and one row represents like their song history, like the history of them playing the song, right? And this will allow you to easily filter based on the user information. You might want to have a materialized view that also lets you do that easy filter based on artist. And then maybe have another view that lets you do it by song title. Now, you could probably get away with using an index for those rather than using a materialized view to completely rewrite that data a second time. But again, the advantage of the materialized view is you have repartitioned the data, right? So now each one of these is on its own node, or every time I see a 5, it's on the same node, right? That's by definition what that partition key is doing, right? So if I are querying by user, I guarantee that when I log into Spotify, I'm seeing my song history. If I make a materialized view by artist, then I am guaranteed that all of the artists are on the same node, right? That's how it differs from an index. It has no other difference from an index other than what I just said, which is now the data has been rewritten on the nodes as well. So, and this has a big impact when you have a large key space, right? Maybe you have 50 nodes in a key space, right? And now you want to have you want to do a little bit of cross cutting, where you want to let someone look at that data by artist or by song title, right? And you could do that with an index, but you're still going to be retrieving the data off several nodes, right? Right? When I indexed on OS and I asked for Windows, it still had to ask a couple of nodes to get Windows because that's not the partition key. If I made a materialized view where OS was the partition key and I asked for Windows, I'm guaranteed that all the Windows nodes, all the Windows rows are coming off one node. So that is the real big advantage of the partition key over the material of the materialized view over the index. All right, I said it. So let me do an example now where I insert something. So I can do insert. I'm going to copy. I'll just type it in. So if I do like insert into system utilization. Whoop. And I'm going to insert host name, OS, measured on, and CPU percentage. I'm going to insert the values. The new host is going to be Earth. It's going to be OSX. And then the date is going to be 2018. Keep things consistent. I think they were all on 7/19. And let's make this at 9 a.m. Oop. And then the CPU percentage was 100. It was pegged. Now if I do this, which is the materialized view, the date is there. See, there's Earth. Okay, now, something to note. If I we're doing this on a real Cassandra cluster with a key space and a ring that had maybe 10 nodes in it, somebody would be connecting and adding this telemetry to. They would be connecting and adding these rows to one of the nodes. Okay, but that one node would say, "Oh, you're talking about Earth. Earth goes here, right? Earth goes here. So if I ask from another node for Earth, I got to spell system utilization right. Should have picked an easier name. I get the data back because I'm asking for the data by its key, right? And its key is it's the partition key, and I'm going to the right partition to get that data. So I don't feel the pain of eventual consistency. Where you're only going to feel the pain of eventual consistency is when you're asking across multiple rows with an index, right? You might be looking at data that's a little late. And again, that's because you aren't fetching it from exactly the right partition key. You might be extracting it from a replica of that partition key. All right, so let's sum up. Index or materialized views. Indexes are fine. The only reason you need to use a materialized view is if you need a different partition key and you want that data copied across your key space differently. Okay? Things to think about when you use a materialized view or you use an index is you're going to have to do additional updates, right? Because again, we know how indexes work. Every index makes reads faster, but also does that by copying data. So now you've increased the write process. It's going to add about 10% overhead to the writes. That's something to think about. So again, indexes are fine unless you want to rewrite that partition key. You want to rewrite that partition key so that the data is spread differently over your cluster, then you're going to use a materialized view. Okay, let's talk wide column database design. So how do you data model with wide column? Well, remember with relational, you can just pretty much model anything that you want. It's very flexible and performant. One table per entity set. You got PK, foreign K relationships, table joins. Data redundancy is undesirable. We want things in third normal form. In wide column, we're going to have a flat denormalized model. You can only query rows based on key data. If you want to filter on non-key data, you're going to need to add a bunch of indexes. One table per query type with related data in the table. No table joins. Data redundancy is expected. So where your process-oriented data is, and then once you know what is your process-oriented data, you want to build a table around that. So let's do an example. Here's enrollment, right? And this is, just kind of like a conceptual / logical sort of mixed together ERD. So you have, students enroll in classes, and then classes are part of courses, right? And the enroll status is like add, drop, withdrawal, right? And so every time you change your enrollment status, it gets added to enrollments. And so if you look at this view here, you'll see it goes one to many, one to many, one to many. So this table here is the sink. Everything is falls into here, right? So this table is the most granular, if you will. You've got a student over here, but they got many enrollments. And you got a class, you got many enrollments. So this table here is the table that when we're going to build wide column, we want to go around that table. Okay. So when you go wide column, you want to think about how you're going to get the information back out. So think about how we might want to do that. We might want to get enrollments, right, by a class. So we want to know who the students are in the class, when they enrolled, when they dropped, when they added, right? All that stuff. So that would be this table here. This table here, enrollments by class, is kind of representing this here. And then it's representing this right here. And then the classes by course, this pretty much is representing this here. So it allows you to search for example, maybe you want to find a room or a semester. Say, in this semester, what are the classes, right? So I might add an index on semester so that you can, find in a given semester what the classes were. This table over here lets you zero in on a student, okay? And so I have my partition key and my cluster key, right? So I'm putting a class on each node, but I'm putting all the students together on that same node. And that makes sense, right? Because you're going to say, here's a class, here's the enrollment, right? And I can read all that easily off that one node. And then when you're querying by course, you're going to once again, you're going to have the partition be the course, IST256, IST769, and then all of the IST769 classes are on that node. And this is useful because then if we add an index by semester, it's still only looking at one node because we chose to cluster them or partition them by course. So if I say IST769 fall 2022 semester, I'm just going to get a list of class numbers for that. And that'll all be on one node because the partition key is by course code. Okay. So you have to think about this when you design. You have to think about, I know my head's in the way. You have to think about your design. What are you going to search for, and where do you want the data to be stored at massive scale? Like right now I've got a one node Cassandra cluster, but one day I'm going to have this massive, if I'm using Cassandra, I'm probably going to have a key space with several nodes in it. So how do I improve performance? I split the data across the nodes by partition key. So the choice of partition key should be the most common way that the data is filtered out, because you're going to have to include that partition key in just about every query. Okay. Why didn't I implement these with one query? It probably wouldn't make sense from a granular standpoint. I could have included a 2-column partition key where you must have the class code and the class number. So IST659 and then, the 5-digit class number. The problem with doing it that way is then I don't get to easily just look across all the different IST659s or IST769s for all these other attributes. So that's why I created 2. One last thing I want to mention is if I do want to search by semester, like it says I cannot search by semester, that's true, but I can always create an index on this and then it will work as long as I'm still including my partition key. But I can't, if I want to search across all semesters, I guess that would work too. It would just be a little heavier of a query once I add that index. And same thing down here. I can search by student name or email if I just add an index. So again, that's what's nice about Cassandra. You can always add the index in there to increase the queryability of your data. What I can't do easily is find out if this student is in a certain room. That is a cross-cutting concern and not capable of doing that. Not with one step. I can use the student to find the class number and then go over to this table and ask the class number for the room. I could do that. Okay. Let's do another example where we, I sort of talked about this a little bit before, but let's talk about building a music playlist in Spotify. So your ERD might look something like this, where you have a user, you log in to Spotify, and then there's some song, Welcome to the Jungle, and then you add that to your playlist. Okay? And I want you to think about this for a minute. I mean, it's pretty simple, right? I have, don't think of all the multiple playlists. Just go with one playlist, right? So user playlist. And then that song gets on the playlist, right? And there's many to many here because I can have like my jogging playlist my I'm working playlist, my I'm getting ready, I'm getting in the zone for class playlist, right? I can have all these different playlists. That's why it's one user, many playlists, and then this playlist song is a bridge table, right? So think about this and ask yourself, how would you design this in Cassandra? Is Cassandra a good use case for this problem? What does Cassandra do that other databases don't do? And why would it make it for a good use case? And what are the queries you use to solve this problem? And then what would you consider using as partition keys? Hey, Spotify uses Cassandra for this exact purpose. We must guarantee rights to allow millions of users to manage their playlists. Reading back a playlist is a personal thing. Yeah, you can share your playlist with others. Move my fat head. You can share your playlist with others, but ultimately, it's a personal thing, your playlist. So remember, queries drive design in Cassandra. So we don't model entities or relationships here. We model the types of queries we want. Okay. And you can't sort. So you just denormalize. You need a song in the playlist. Playlists are personal to users. So partitioning, you partition by user, right? Maybe you partition by user and playlist, right? Think about that. So on a node is not only it's not only a playlist, it's your playlist. So I need not only your user ID, but also your playlist ID. And then the cluster key would be either the order of the songs on the playlist or the date or time they were added to the playlist. And then we can add an index that deals with the preferred order of the playlist. So I could have columns like user ID and then another column of user info with like email and name and all this other stuff. And then playlist ID, and that would be the partition key, and then playlist name. And then I would have a cluster key that would tell me the song order, or maybe it could be the time it was added to the playlist. And then the ID of the song, and then some info about the song, like the title and the artist, and maybe a pointer to where I could go play the song. And that primary key here would be user ID and playlist ID. So that way I get on a node, when I read in my entire playlist, it's reading it off of one node. When I read in some other playlist, it's reading again off one node somewhere. And the fact that I use both of these as partition key, one playlist might be on one node and another playlist might be on a different node, but really kind of who cares? As long as I'm being personal and reading it off that one node, that makes sense to me. All right, let's talk updates and deletes in Cassandra. So updates, we saw that an insert is really an upsert. Cassandra has an update statement. We can use it to manipulate sets of data. There's no batch updates. There's no bulk updates. You must include a row key when doing an update. There's no way to say update all these and add one to some value. You can't do that like you can do it in relational. You must include the entire row key to do an update. So update table, set column to value where your key column equals your key value. Deletes, you can delete from an entire row like an RDBMS, like delete from table where key equals value. But what's also cool about wide column databases is you can delete columns. You can say delete column from table where row equals value. And in this case, it would just delete the one value in the cell. So it's kind of like doing an update and setting null in an RDBMS. But remember, because each column is really stored in its own table, technically, this is a very trivial operation for a wide column database to do, to delete an attribute out of a column that's in a table, right, by its row. Let's do some examples here. And while we're at it, we will show you how to use different data types in Cassandra in the same process. All right, here I am again out at the command line. Let's get going here. So I'm going to alter the table system utilization, and I'm going to add a column here, and I'm going to add a column called app list, and that's going to be a list of text. So the data type is going to be list of text, like that. I guess I will describe so that you can see that now there is a column called app list right there. Okay, and so this will also get you familiar with how to make lists of data in Cassandra. So let's do this. Let's add, if I do select, I do a select here from system utilization, you'll see that there's no apps in the app list. So at this time on Venus, what was running on the apps? What was running in apps? So let's do this. Let's say update system utilization. I'm just going to do it like this. Update system utilization. Set app list equal to, let's say that Word and Notepad were running. Those two apps were running. Where host name is Venus and the measured on, I got to specify the entire row key is, and I'm going to just copy that. You don't want to watch Uncle Mike. There we go. And I got to spell update, right? There. And then let's take a look at what we did. So now you'll see that this row has been updated. Another way that I can do this is I can do it like this. I can say update. I can do it kind of like this. Update set app list. No apps running. And let's say later on where the CPU percentage is 0, right? So at 10 a.m., there were no apps running. And no apps running still comes back as null. See that? Still comes back as null. So this is the same as null. So that's a little different than relational, which is kind of nice, really, actually. I mean, that's one of the pains in the necks about relational is what's the difference between empty and null? There's a subtle difference, right? And so in here, there isn't. It's good to know. And then when the CPU was 15%, let's change it around. Let's say when at 11 o'clock, the apps that were running were Excel and Chrome. And let's throw in for good measure Notepad. There. Okay, so it gives you an idea sort of how that works. What else can I show you? Well, I can show you how delete works, right? So let me do this again. Let's pick Mars. Let's just say that Excel was running on Mars. Okay, and then, whoops, I made a mistake. Excel wasn't running on Mars. I want to delete that, right? So I can do delete app list from this way. Delete app list from system utilization. I can't do this, by the way. This just doesn't. I need a where clause. Okay, where again, unless you specify a row key, none of these updates going to work. And then I can say where. I guess I'm going to just try and do it this way. Delete app list from system utilization where that. And then that gets rid of, if you want to pay attention to this row right here, that's how you get rid of a value in a column. See that? Ta-da! Right? That's how you get rid of a value in a column without deleting the entire row, which is what you might not want to do. Okay? And that's how you do updates in Cassandra. All right, let's talk how you can integrate Cassandra with Spark. So in Cassandra, you will require a table before you can do anything with Spark. So you cannot create the table in Spark at all. Spark does not support the Cassandra query language. So you must build the table first, either in Python or from the Cassandra client or from some other Cassandra client. But then after you have the table made, you can query it pretty easily like it was in a data frame. And when using append mode, Cassandra will support upserts. So this is pretty nice. Okay, let's not forget about some anti-patterns that may happen in Spark, right? Don't do anything that doesn't use the partition key. Okay, make sure you're still using that partition key, because if it doesn't, it'll still run the query for you. Doesn't care, but it's going to be doing, it's going to be turning allow filtering on, which means that you're going to be asking a lot of the Cassandra database. Okay, again, anti-pattern, avoid it. Design your Cassandra database correctly. Use the partition key. You can query in Spark and not use the partition key, and that ends up being a little dangerous. Okay, let's do a demo in Spark, and let's just do a couple of really simple demos and show you how Cassandra and Spark play together. All right, I am out here in Jupyter, and what you're looking at here is the wide column example in work content. That's, by the way, where all of these commands were that you saw me typing. And I'm going to initiate my Spark session to connect to Cassandra. Okay, we're good to go there. It's getting the jars I need. It's downloading the plugins. And now what I'm going to do is I'm going to come down here to this cell, and this cell is going to make a key space called GDemo, and it is going to make a table in here called FudgeMart order details. Okay, and this is not using Spark. This is using a Python library called Cassandra Driver, which allows me to type in any SQL I want, SQL I want, and then it runs it on my Cassandra cluster. So I'm going to do that, and then what this is going to do down here is it's going to read in FudgeMart order details from the local data set, put it into some kind of Spark data frame, and then it's going to write it out to Cassandra. Okay, I'm going to do that first. Grinding away, grinding away, grinding away. And we're done. Okay. Now, let's go see what we did. It's a key space called GDemo and a table called FudgeMart order details. Let's go dig it out. So use GDemo. Select. And there you go. There's a bunch of data in here. See that? And there's a lot of data in here. And that's very Cassandra-like. And you probably aren't going to use select star from a table like this in real Cassandra. Let me describe it. And you can see there's a lot of columns in here. See that? And the primary key is customer ID and order ID are the partition key, and then order item ID is the cluster key. All right. Now let me show you a couple things about Spark and Cassandra that I promised I'd show you in the demo. So let me load back the table into Spark. Okay, and then there's the schema, right? Now I can filter on that partition key, right? And when I do that, and I look very carefully, let me zoom it in. Look very carefully, you'll see that it is passing the Cassandra filter in to Cassandra. And this is a good thing. So it's asking Cassandra to do this, right? Watch what happens when I try to filter on something that doesn't use the partition key. It does not pass a Cassandra filter in. Okay, so what does this mean, right? I guess rather than explaining it, I can show you, right? Oh, there's the order. Yay, it works, right? The nice thing about looking at this order right here, this order uses the partition key of Cassandra, which means it's only asking one node for this order. That's good. This down here, where I asked to see everything shipped by postal service, I can do this, okay? And it runs pretty efficiently, and I see output, but you got to understand, if this were a real Cassandra key space with hundreds of nodes in it, because the data volume is incredibly large, this query would take a very long time, because it would have to ask all the nodes who's participating in this query. And it can't do that reasonably. So instead, it sends all the data to Spark, and then Spark does the filter. So you're not even leveraging the value of Cassandra in this query. So just because you can do it doesn't mean you should. And again, this is like the theme of this course. I can make Spark do anything I want, but I need to know when I'm using Spark and when I'm using the underlying DBMS that's talking to Spark. Because ideally, I want to send my column projections and my filters to the underlying DBMS and have that do the work. And then what comes back to my Spark cluster is far less. It's unreasonable to ask Cassandra to give you everything and have your Spark cluster try to swallow the fire hose that is all the data off your Cassandra cluster, just so you can figure out which ones were shipped via postal service. Okay, that is an anti-pattern. That is not big data. That is doing it wrong. That is doing it small data. Okay, and you can't think like that. Okay, so that's the number one theme to get out of what we've been doing so far in the entire course and right now with Cassandra is you got a partition key, you got to use that partition key. Okay, if you want to ask for the data and it's not using a partition key, you better have an index on it. Okay, if you have an index on it, it'll use that Cassandra filter. Okay, let's sum up this unit. Wide column databases store data in individual columns under a row key. Common use cases for wide column include high volume write scenarios at scale, like orders, telemetry, right? Most suitable for process-oriented and time series data, generally stuff that we're going to write once. We can write it multiple times, but that's really kind of not the point. We saw also that Cassandra is incredibly graceful with adding the same data with the same matching key more than once. It just does an upsert. Cassandra uses a ring architecture, which means there are multiple nodes and that the data is going to be eventually consistent, which means that the data written to a specific node will be consistent, but if read off another node, it may not be accurate at that point in time. Cassandra has a SQL-like query language called CQL, And select queries must include the partition key. Yeah, you can write a query without the partition key, but in doing so, you incur a heavy cost to the Cassandra query, as it has to lift pretty much all the data off of each of the nodes in the ring, or at least enough of the participants in the nodes in the ring to cover the data set. You can use indexes and materialized views to get around the fact that you want to query the data by something other than the partition or cluster key. And it will allow you to do that. Just remember that with Cassandra, you have to do a match, an exact match. You can't do greater than or less than. You have to do equal to. You can't even do not equal to. The only options really available to you on a key match is equals or in. Spark has support for Cassandra and the ability to pass through queries based on the filter, from the filter in Spark to Cassandra, and it will use whatever index or keys you have set up accordingly. And you just have to be very careful to not do something there that is going to request more data than you want from Cassandra, because Cassandra has no way to filter it.